Hello everyone, my name is Mariam Gurab and this is my Module 8 final project. The topics we will be covering today include the real-world applications of optimization and of differential equations. So just to give a brief overview of what optimization is, it's the process of finding an absolute minimum or absolute maximum value of a function given a set of constraints. And the steps to optimize something include determining what needs to be optimized, writing the equation, performing the first derivative test, finding the absolute extrema, and concluding. So how can optimization be used in the real world? Well, let's look at the following example. A townhome complex has 250 homes to rent. If they rent X townhomes, then their monthly profit in dollars is given by P of X. How many townhomes should they rent in order to maximize their profit? The first step we need to do here is to perform the first derivative test on P of X and to find the critical point. When we do this, we find that X equals 200. Now we need to compare 200 to the endpoints of 0 and 250. When we plug each of these values into P of X, we find that renting 200 townhomes yields the most profit of $240,000. In the previous example, we saw how optimization was used in the business and finance world. Optimization can also be used in engineering. For example, an industrial engineer's role in a business or firm is to optimize, whether that be optimizing resources in order to lessen production costs or finding ways to optimize and improve a business's production methods. Industrial engineers use optimization daily. So just to give a brief overview on differential equations, when solving for differential equations, you are solving for the original equation. The steps involved including separating the variables, getting dy and y on one side and dx and x on the other, integrating both sides of the equation, and solving for y. It's important to remember that when solving for a specific point, don't forget to solve for c. So how can differential equations be used in the real world? Well, let's look at the following example. The temperature of a body dropped from 200 degrees to 100 degrees in the first hour. Determine how many degrees the body cooled in 1 hour more if the environment temperature is 0 degrees. So the differential equation we are provided with is dt over dt equals k times t minus 0, with 0 representing the environment temperature given. This is Newton's law of heating and cooling. To solve for t, we must separate the variables, integrate both sides, and solve. Because of our extensive use of Newton's law in class, we know that t equals ae to the power of kt. After plugging in the conditions given to solve for the missing variables, we find that in between hours 1 and 2, with an environment temperature of 0, the body cooled 50 degrees. In the previous application, we saw a prime example of how differential equations are used in the field of forensic science. Forensic scientists collect and analyze evidence in crime scene investigations, and to do this, they heavily rely on chemistry, math, and biology. In homicide investigations, forensic scientists use Newton's law of heating and cooling and differential equations to find the time of death of a victim. The following sources I used were for application problems and job descriptions. Thanks for watching my video.